Today we'll start with this design of bolted joints. As you know, this bolted joints are actually this joints which are detachable joints, right? So this is not permanent joint, right? So this is actually considered as threaded joints, right, which can be separated, right, as in when required, so it can be disassembled, right? So there are various types of this bolt, right, as it is mentioned in the figure. This through bolt, then tap bolt and stud. So as you can see, the difference is here in case of this through bolt, the bolt is throughout the plates which are being joined, right? Suppose if this plate 1 and 2 are being joined with the help of this bolted joint, so in that case this bolt is passing through the length, or you can say the thickness of this both plate, and at the end it is being fastened with the help of this nut, right? So this is actually bolt head, right? And you will have threads, right, which will be utilized for making this joint. So after that, this tap bolt, it means here in the second case, the one of the part which you are joining with the help of this bolted joint will have internal threads, right? So that is why it is known as this tap bolt. So this particular component, let us say, are having internal threads, right? And here again you will have this bolt head, and here you will have thread in this particular portion of the bolt, and here nut is not required, right? While the last is this stud. As you can see here in this case, you are having the thread at the end of this particular length of this stud is basically cylindrical what we can say component which are having threads at it both ends, this end as well as this end, right? So at both end it will have threads, and generally it is found in this engine blocks and all this kind of studs, right? So you will have this thread, and here you will have again tap, right? And here at the other end you are going to use this nut in order to have joint, right? So this is how you will have right. So this is how you are having this various types of this bolted joints, right? Apart from that, actually you are having screw also. In screw generally you are not using nut, right? Simply you will have the internal threads on the mating part. So you can have the cap screw, and then what we can say set screws and all are there. There are different types of it are also discussed, right? But we are not discussing all this different types of
मित्र
caps.
कहाँ कहाँ है
Sorry,
मतलब
mute yourself. Hello. Okay. So now, so those types of cap screws and types of set screws are also there. It is given in that book of that Bhandari, but we are not discussing all this at length. So we are coming to directly this bolts of uniform strength. Now, what do we mean by bolts of uniform strength? Actually, whenever any load is applied on this bolt, so as you can see here, you are having this threaded portion, as you can see, right? And here you are having this shank diameter, right? So basically whenever we apply any load, it will be distributed among this threaded portion and this shank portion. So in threaded portion, as you can see, the diameter is not uniform, right? Diameter is not uniform in this threaded portion, and here stress concentration will also be there, right? So here you will have core diameter and major diameter or nominal diameter, that you will see the terminology of threads, right? So here you will have a core diameter which will have the highest stress in this case. So if the highest stress is in that region, then the maximum amount of the energy beared or the strain energy absorbed will be by that particular portion, right, of your this bolts. And in this shank diameter, as this diameter is larger than this, the capability of absorbing that shock will be less in comparison to the threaded portion. Actually this is not desirable, because as we can see along the length of the bolt, we are having variation in strength, right, or we can say stress applied, right? So actually this portion of your bolt will go under failure at different stress, and this particular portion of this bolt will go at failure under different stress. That is why here you are not having uniform strength. But in order to achieve the uniform strength, generally this shank diameter is made equal to the core diameter of the threads, right? Or you can also have a hole, as it is mentioned in this figure, right, of diameter d1, which will be helpful in attaining the uniform strength throughout the length of the bolt. Now if you see that how this d1 is achieved, then if you can see this pi by 4 d square, right, minus pi by 4 d1 square will be equated to that pi by 4 dc square, right? Why we have equated this? Because we want uniform strength, right? So uniform strength will be that stress into area. So we have equated area of this both portion, right, this portion and this portion, right? At this portion the stress will be calculated with the least diameter, that is this core diameter, and here you have now this relation or this area, right, left in this region, pi by 4 d square minus pi by 4 d1 square. So if you simplify this, then you will be able to calculate the required diameter d1, which will give you almost uniform strength throughout the length of the bolt. So this d1 can be calculated from under root d square minus dc square, right? So here what is this d and dc? D is the nominal diameter, right, or major diameter of thread, while this dc is core diameter, right, or the least diameter, right? So this is how you are having uh, your diameter d1, which is required to be drilled in order to achieve this uniform strength in your bolt, right? So after that, if you see this terminology of screw thread, then this major diameter and minor diameter, as we have discussed,
So,
right?
so,
Yes.
that stress concentration on the threaded portion will be uniform. How can it be uniform at threaded portion?
Sorry.
Stress concentration at the thread. You have written the stress concentration at the threaded portion is uniform, isn't it?
No, 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 no. What we have discussed is the strength of the bolt should remain uniform along its length, right? So
Okay, so,
here, yeah. So here, whatever stress is going to make failure in this region, also the same stress should make failure. That is why these bolts of uniform strength we are preferring, right? Are you getting?
so we
Sorry.
so we reduce it at what are we doing to reduce the stress concentration, make it uniform?
See, here we are not reducing stress concentration, right? What we are making sure is whatever maximum stress is generated, right, in the portion of threaded region will be the similar in the region where these threads are not applied along the length of the bolt. Okay.
Okay, sir.
Okay.
So will we do anything to make it uniform?
So that is
I
what
mean,
we have done. Now we have calculated the diameter of D1, which needs to be drilled, right? So that the what we can say, the stress generated in that region will also be similar to the stress beared by that threaded region.
okay, so there is a fillet given in the region.
Sorry.
On the second figure, on the second figure there is a fillet region nearby. Uh,
Sorry. Which figure?
you have given three figures there, isn't it? I mean,
This
A,
A,
B,
B, A.
C. Is it different steps so what I ask is, A and B and C are the different stages. Is it like different stages, or is
It is different
A, B, C?
different construction of your bolt. A, B, and C are different construction of bolt. In figure A, your bolt is manufactured with shank diameter as D, right? And you are having your thread configuration or thread characteristic as it is. It will have that major diameter as D and that what we can say, that root diameter as that DC. So what will happen in this case is your this threaded portion will have a higher stress resulted, because stress resulted in this different region will be given by P by A, right? If you say this as let us say P1 A1, right? Here you will have the
Yes, sir.
same force, but area will be A2, right? Or A2,
Yes, sir.
right? So in this region 1, stress experience will be more in comparison to the region 2. So that strain energy absorbed will be more in the region 1 in comparison to region 2, right? And stress value
Yes,
will also be higher in the region 1 than region 2, right? What we want is, whenever any force applied to the bolt, it should be uniformly distributed along the length of the bolt, right? That is desirable. So there are two different things you can do, case A and case B, right? Case A is you are reducing the whole shank diameter to that DC, right? So the maximum stress generated here is based on that pi by 4 DC square, right? So that is one option, right?
yes, yes,
So
sir.
that the stress generated will be similar throughout the length. The second option is B, that you are drilling the whole of diameter D1, so that you make that area which is equal to that pi by 4 DC square. So the stress generated will be again similar to the region of the threaded region, and hence you are getting the similar strength of both the region. Are you getting?
Yes, sir.
Right. So these three are different what you can say, method of manufacturing bolt, right? One is keeping this shank diameter throughout the length of bolt where threads are not there. The second is you are reducing that diameter to DC, right? And third is you are drilling a hole. I guess it is clear, right?
Yes, sir.
Okay. Now
Sir,
terminology of screw, yeah.
sir, please explain the third case, sir.
Yeah, so third case again, as I have told you, this we are considering as region 1 and this as region 2. So our aim is to have similar stress generated in both the region. Right, you are
Yes,
applying
sir.
the same load to both the regions. So if area will be same, then stress generated will be same. It is obvious, right?
Yes, sir.
Yeah, so here in region 1, the minimum area on which the stress is going to be generated or stress is going to be induced is pi by 4 DC square.
Yes, sir.
Right, and in the region 2 your area is pi by 4 d square minus pi by 4 d1 square, right?
D1. Yes, sir.
Right, so from this relation you can get the required diameter d1 needs to be drilled in the region of this shank, right?
Yes, sir. Yes, sir.
And okay.
Yes, sir. Thank you, sir.
Okay, so now next is this terminology, right? So in this terminology of screw thread, as we can see, you will have this major diameter, minor diameter, right? And then pitch diameter, this thread angle and pitch. This all are very common things, right? Crest and root. Crest and root will be difference in case of external thread and internal thread, right? In internal thread, you will have root, where in external thread you will have crest, right? So vice versa in this external thread, this is external, right, and this is internal. So here crest is at this point, right, while here root will be there at that point in case of internal. So this is how the terminology of thread is there, right? Then you have this ISO standard, right? Here again the same thing is discussed, but with some relation, right? It is discussed. And then this designation of the screw thread is there. Generally this fine series you are using this M6 by 1, so it means 6 is the diameter of this what we can say head, and this nominal diameter or major diameter is this 6, and this 1 is the pitch, right? So this is some preliminary things regarding this threads, right, and bolted joints. Now
Sir,
if yes.
sir, why mostly used the ISO thread and include angle 60 degrees, not remaining the ACME thread, knuckle thread, butter thread? Why most used the include angle V thread profile 60 degrees only, sir?
uh, Actually in this whatever the strength is achieved is, I guess, optimum. That is why we are generally going for this metric thread, as it is mentioned here, 60 degree in ISO standard, right? Because we are providing this fillets and all are also in order to reduce the stress concentration in the threaded region, right?
Okay, sir.
Okay, so for now, if any force is applied on this bolted joint, as it is mentioned in the figure, then the stress generated will be this load applied upon the minimum area, which is, as we know, at the what you can say, the core diameter pi by 4 dc square, right? And we also know that this tensile stress is given by the tensile strength of material upon factor of safety, right? So from this you can come up with the strength of bolt like this. P will be equal to pi by 4 dc square into the sigma t can be replaced with syt upon factor of safety, right? Now when a nut is pressed against this bolt threads, then it is going to experience some shear stress, right? And the shear stress will be experienced at that core diameter, again that dc, right? And let us assume the height of nut as h. So if we assume the height of nut as h, then area available will be that pi dc into h, right? And as we are discussing about the shear stress, then it will be tau, and tau is given by shear strength upon factor of safety, right? So again, as you know, the shear strength will be half the ultimate this tensile strength. So you can still go for simplification, that is 0.5 syt upon factor of safety, right? Now if you compare this 1 and 2, right, then you will come up with the relation between the height of the nut, right, and this diameter dc, because as you can see, if you compare this 1 and 2, that is pi by 4 dc square syt upon fs will be equal to this pi dc h into 0.5 syt upon fs. So now if you simplify this, then you will have this dc equals to, or you can say this h equals to 0.5 dc, right? And as we know, this dc core diameter is 0.8 times the nominal diameter, right? So through this you will come up with this height of nut equal to 0.4 times the nominal diameter, right? Generally the nut are being built with the height of 0.8 times nominal diameter, right? So Based on this you can calculate this simple numerical, right? So in this what it is asking is an electric motor weighing 10 kilonewton is lifted by means of an eye bolt as shown in the figure. The eye bolt is screwed into the frame of the motor. The eye bolt has coarse threads. It is made of plain carbon steel 30C8, right? And the factor of safety is 6. Determine the size of the bolt. So here it is very simple, right? So whatever we have discussed, right, based on that you can attempt this question. So how will you start? Anyone?
Stress is equal to force by area.
Sorry?
10 kilonewton divided by area.
Yeah. So stress, you will say that stress, whatever tensile stress generated will be the force divided by area. And as you know, area we will consider at the core diameter, so that will be pi by 4 dc square. And this stress will be whatever the maximum stress is given, that is, or strength is given, tensile strength, that is 400 divided by factor of safety, right? And you also know the load, right, which is given as 10 kilonewton. So now, having all this details with you, you can come up with the DC, right? So what is DC? Anyone?
$13.8
Yeah, it is
mm.
almost 13.8 or 13.82 mm. Right, once you have DC, then you can go to the nominal diameter. So nominal diameter is DC divided by 0.8, right? So that will give you around 17.27, right? So you can take it as almost 18 mm, and in the ISO standard it will come to that M20 series. Okay, so is it clear?
Sir, if we have to consider the shear strength, then the area will be the 2 pi r L by 2, because half of the portion will be of other thread.
Sorry?
सर मतलब कि अगर shear stress को consideration में करते हैं तो area will be like 2 pi r into h by 2.
Area will be that pi dh only, na? Shear area will be.
So shear area for the given bolt will be half, because half of the portion.
Here we are directly considering this tensile strength only, right?
Sir, if we are to consider shear strength, then it will be half of that, na? 2 pi RH by 2.
I guess no, it will be the same actually. That pi dh will be the area that you have to consider for the shear stress, because the whole area is going to resist that particular force, right? Or it will be generated
Sir,
in
I
that
think,
full area, right?
sir, in shear strength, I mean for shear stress, the shear strength will be half of yield strength.
That is correct.
नहीं सर, मैं वो नहीं कह रहा, मैं कह रहा था
Here he is telling something different.
Sir, because the portion in which the thread is present is almost half of the, क्योंकि आधे portion में है नहीं thread, आधे में है.
No. It is not like that. It will be different, right? The shank length and the thread length are not always half and something like that. It is not like that.
Okay, sir.
Okay. So let us go to the next one. Right. So in case of this eccentrically loaded bolted joint, we have to go through some similar things which we have seen in that welded joint, right? We have to transfer this load to this geometric center, right? This P, and along with that the moment generated because of this force it is applied at some eccentricity. So you will have this moment P cross E as we have done in that welded joints, right? So here in this figure it is given that if you are having a system of 5 bolts, then you have to go for actually calculation of this X bar and Y bar, as you know that sigma AI XI upon sigma xi, and for Y bar it may be sigma AI yi upon sigma yi. If it is the case, then you have to go and calculate first the geometric center, and then you have to transfer the load to this the center of the geometric center, right? So here in this figure 7.16 you are given this symmetric system, so this G will lie at the center of this bolted system 1 2 3 4. So you can directly transfer the load which is acting at some eccentricity E to this particular center G, right? But along with that you will also have this moment generated, that is P into E. Now having this situation, what what this particular joint will experience is primary and secondary shear stress, right? Primary and secondary shear stress will be generated, right? Primary and secondary shear stresses will be generated. The first will be due to this force, right, which is going to be equally applied on all the bolts. So this P by number of bolts, right, that will be applied to this all 4 bolts, right, that is P1 P2 P3 P4, right? And the other force, secondary force, which will be obtained or which will induce because of this moment which we have transferred, right, due to eccentricity. So here you will have this P1 dash R1, P2 dash R2, P3 dash R3 and P4 dash R4. So here if you see here they have considered some different notation, right? Instead of that P1 and P1 dash, here it is P1 dash and P1 double dash, right? So let us go with that only, right? So let us not have any confusion. So here they have written like this: for primary it is P1 dash, for secondary it is P1 double dash, right? So as you can see, this P1 double dash or P2 double dash or P3 double dash or this P4 double dash all are acting perpendicular to the distance from the CG, right? Here it is acting at this R1. So the moment generated will be this P1 double dash into R1, and it is going to oppose the moment which you have transferred to the center, that is P cross E, right? So at each point it will be in this direction only, which is going to oppose this clockwise which we have transferred to the this center. So for P2 double dash also it is in anti-clockwise, for P3 double dash also it will be in this anti-clockwise, similarly for P4 double dash also it will be in anti-clockwise or counterclockwise. As this is clockwise, all the other moments will be counterclockwise movement, right? So now the thing is, this particular force P1 double dash or P2 double dash are at varying according to the distance from this particular geometric center, this G, right, or center of gravity, that G, right? So so that is why this P1 double dash can be mentioned as CR1, or as it is varying proportional to the distance from that centroid. So P1 double dash is actually varying as R1. If R1 increases, it will vary. So P1 double dash can be written as CR1, and so all other, right? P2 double dash can be written as CR2, P3 double dash can be written as CR3, P4 double dash can be mentioned as CR4, right? So if you put all this equation or all this relation in the above equation, right, then what you will get, this P into E equals to as we are replacing this P1 double dash with CR1, what you will get is this CR1 square. Here P1 double dash will be CR1, and already we are having this R1, right? So as already we are having that R1, then it will be CR1 square, similarly CR2 square, right? CR3 square and CR4 square. Now from this actually you will be able to get the value of this C. So then C can be written as P cross E upon this R1 square, R2 square, R3 square and R4 square. So if you put the value of this C into all that P1 double dash, P2 double dash, P3 double dash, then it will be PE R1, right, upon R1 square, R2 square, R3 square and R4 square, because it is CR1 and C is PE upon R1 square plus R2 square plus R3 square plus R4 square. Similarly you can write for P2 double dash, P3 double dash, P4 double dash and so on, right, whatever number of volts we are using. So from this understanding you can calculate this simple problem. Here the structural connection shown in figure 7.16 is subjected to an eccentric force P of 10 kilonewton with an eccentricity of 500 mm from the CG of the bolts. The center distance between the bolts 1 and 2 is 200 mm and the center distance between bolts 1 and 3 is 150 mm. All the bolts are identical, right? The bolts are made from plain carbon steel. The factor of safety is 2.5. Determine the bolt size, right? So if you see here, I guess this figure is itself the 7.16, right, which is mentioned in that particular what you can say problem, right? So I guess, and now it will be easier for you, right? Right, so now you can attempt this problem, right? Yes. So how will you start?
Finding primary shear force and secondary shear force.
Yeah, so you can start calculating that primary and secondary shear force. Primary shear force will be this 10 kilonewton by 4, right?
Yes, sir.
Right, so this primary for all will be this P1, P2, P3, P4. It will be equal to this 10 kilonewton by number of poles, so that is 2500 Newton, right? Then for secondary shear force, as we have derived, it will be same in all, right? Because here symmetricity is there. So PE R1 square upon R1 square plus R2 square plus R3 square plus R4 square. Please mute yourself. So here R, I guess you need to calculate first, right? So if you consider this, suppose this, let us say if you are considering this P1 double dash, which is acting this, then this will be the R, right? Or R1, R2, R3, R4 all will be R only. But you have to calculate this based on the data given. So what is mentioned as this distance and this distance? So between 1 and 2 is 200, right? So this distance will be 100. and between 1 and 3 is 150, so this distance will be 75. Yes, correct? Right, if this 1 2 3 4, the distance between 1 and 2 is given as 200. This 1 2 3 and 4, so distance between 1 and 2 is given as 200. 1 and 3 is given as 150. The distance from here, with this r you are going to calculate, then this will be 100, this will be 75. Yes or no?
Yes, sir.
So here in this equation, this r1 r2 r3 r4 all are r only actually, right? So it will be per upon 4r square, so it will be almost equal to the pe upon 4r. R you can calculate with this data. P and P are already provided. So you can tell me what is this P1 double dash?
$10,000.
Newton.
10,000 Newton, yeah, correct. So as all bolts are at equal distance, we need not to find that which bolt is under maximum force, right? So at all it will be same. So now what we need to do is we need to calculate the resultant force, right? So how can you calculate that resultant force? See, P1 double dash will be having components, right? This P1 dash is the acting opposite to this, right? As you can see, this P1 double dash is acting at certain angle, but this P1 dash is acting opposite to this force, right? P. So this will make the same angle, right, as the angle made by this theta here, right? Whatever this theta will be, the same theta will be here. So this theta can be calculated with tan theta, right? Tan theta can be equated as 75 by 100.
So,
Sorry?
so how will we determine this direction of P1 dash and P1 double dash?
See, P1 dash is the simple, it will act directly opposite to this applied load, right? And how
Yes.
P1 dash is identified, or how the direction of P1 dash is identified, is as we have seen earlier also, as this P1 is acting in this direction, when you will transfer it to this G, it will generate movement in clockwise direction. So P1 dash should have the direction which is going to generate the moment opposite to this P cross E, right? So then this is the only direction, right, P1 double dash can act, so that the moment generated is going to be in the opposite direction to this P cross E. Are you getting?
Yes, sir.
Okay. So based on this, now what you can have is this theta you can calculate as we have discussed, right? 75 by 100. So from that you can have this P1 double dash cos theta and P1 double dash sin theta. So what is theta?
Sir, 36.86.
36.86 or somewhat like that, right? So
Yes, sir.
yeah, so basically once you have this theta with you, then your horizontal component and vertical component will be this P1 double dash cos theta minus P1, because both are in opposite direction to each other, right? So this P1 double dash cos theta minus P1 dash, right, plus this P1 double dash sine theta. This both components will be squared, right, and taken under root in order to have resultant, right? Here, as we are considering this P1 dash and P1 double dash, so P1 will be the resultant. Actually, we need to calculate at point 2 also to make sure that whatever P1 is coming is similar to that or having some difference. So what is
The P1 is 8139, sir.
yeah. So let us write for this P1
8139.09, sir.
yeah, it is almost equal to 8139 something Newton, right? Now
Yes, sir.
if you consider
Sir, but our focus should be on the highest, मतलब जिसमें सबसे ज़्यादा load.
yes. So let us go for P2 also. In case of this P2, what do you think the direction of force? Can anyone tell?
One 135 degree from x axis, मतलब
Like
x
this,
horizontal.
like this, right? Correct?
Yes, yes, sir.
Correct. So here in this case, this P2 is actually directly acting at that angle theta only, right? Where is whatever we have calculated, this theta, right? Yes or no?
Yes.
Right. So as this P2 double dash is acting at that angle theta, right? So this actually here to here, let us say. So no, not this angle will not be theta, sorry. Let me write this way. Right, as here we have considered this angle as theta, right? This one with vertical. So here also this with vertical, this will make that angle theta. Whatever angle is made here, right, the same will be made with the vertical. So P2 double dash cos theta now is going to be added to this P2 dash, because here we are having P2 dash, right, and this P2 double dash cos theta. So in case of that bolt 1, they were in opposite direction, P1 dash and P1 double dash cos theta, but here in case of this P2, both are in the same direction. Are you getting what I am saying? Hello?
Yes, sir. Yes, sir.
So if you calculate this for P2, then for P2 resultant will be this P2 dash double dash cos theta plus P2 dash square plus P2 double dash sine theta square. Yes. So from this you can have your P2. So what is P2? So this P2 dash and P2 double dash are same as P1 dash and P1 double dash, right? P2 dash is 2500 and P2 double dash is 10,000. So can you tell me what are you getting as this P2?
12,093.
Yeah, correct. So it is around this 12,093, right, approximately. Once you get this, you can check or you can observe that this P2 is greater than P1, right? So this bolt 2 and 4 will experience the highest load. So based on that, shear stress generated will be higher at this point. So if you consider this tau is equal to this P2 by A, then tau is given as 80, right? And you have calculated this P2 as, let us say, 12093, then divide by pi by 4 dc square. So it will give you dc. So what is dc?
The 19.87.
Sorry?
13.87, sir.
Yeah, it is almost about this 13.87. Again, if you will go for major diameter, then it is dc by 0.8. So it will give 17.34.
17.34, sir.
Yeah. So almost 18. So again you can go for this M20, right? So this is how you are having your selection of bolt, right, based on the different forces, right, and different stresses which we are considering, primary and secondary shear stress, right? Once you are done with this, then one more case you can consider, that if this load, right, which is eccentric, is perpendicular to the axis of bolt, right? Here you are having this axis of bolt. So in this case, load acting is perpendicular, right? As you can see, load is acting here and the bolt axis is this one, right? So it is acting perpendicular to the bolt axis, right? So this front view and side view is mentioned in this figure A, right? So now what happens when this load is going to act? So in that case, this bracket will undergo deflection, right? And this deflection will be actually what we can say proportional to the distance from this particular point C, as it is mentioned here, right? So here also you will have primary and secondary shear stress, right? But here also, as you can see, this number of bolts are 4 right here, but they have mentioned both lying at similar location as 1 and other as 2. So this P1 dash is equal to that P2 dash will be again whatever total load applied by number of bolts. This will give you primary shear stress, right? So once you are done with the calculation of this primary shear stress, then you need to calculate the secondary shear stress, right? But here, as what we have first observed is this deflection is proportional to the distance from that point C, right? So delta 1 is proportional to, means delta 1 is more in comparison to delta 2 because L1 is higher than this L2, right? So now using this particular what we can say dependency, you can also derive that forces are also proportional to this distance from the this point, pivot point C. How? Because as we know, this force is proportional to stress, right? Because this force is given by stress into area, right? The stress is dependent, or it is proportional to strain, right? This sigma is equal to the Young's modulus into strain, right? And then again, strain is dependent on the deflection, right? Or you can say stretch, right? So that this deflection or stretch is again delta by L, right? So again this delta has come into picture, which depends on that L1, right? So you can also write that secondary shear force will also dependent or proportional to the distance from that particular point C, right? So as we have written that P1 double dash is equal to CR1 in previous case, here also we can write that, right? So once you have this, then you can actually again write, as we have gone for that equilibrium of moment. Here also you can go for equilibrium of moment, right? That PE. So if you write for equilibrium of this moment PE, then it will be equal to 2 times this P1 double dash L1 plus 2 times P2 double dash L2, because these 2 bolts are there at that position, right? And if you put this CL1 and CL2, then what will you get? You will get it as this 2C L1 square plus L2 square. So from this you can actually write what is C, that is equal to PP upon 2 L1 square plus L2 square, right? So once you have this value of C, it will help you in calculating the secondary forces, right? That is PE L1, right, upon 2 L1 square plus L2 square, and so on. You can write for the P2 dash also, that is, for P2 double dash also, that is PE L2 upon 2 L1 square plus L2 square, right? So as we know, with this particular forces which we have calculated in this case, this force P1 dash is going to generate shear, right, in the bolt, right? As you can see here, this P1 is going to be opposed by the force P1 dash and P2 dash, which is going to generate shear, right? While the force which is opposing this moment, right, will be in this direction, right? So as it is this clockwise movement again, P cross E, right? So the force generated due to this moment which is going to oppose it, right, will be in this direction here and in this direction here, because then only it can oppose the moment generated. So this force will be in the form of this tensile force, right? So it will generate tensile stress. So in this case you have to consider this different thing, right? Because the nature of stress is different. So here tau will be this P1 dash by A, while this sigma T will be this P1 double dash by A, right? So once you have the value of the shear stress and this tensile stress, then you can use either MPST or MSST, right, as per the material used, right? So this MPST will be with this sigma T by 2 square plus tau square plus sigma T by 2, right? While the shear stress will be simply this sigma T by 2 square plus tau square. So this is how you can have the sigma 1 and tau, and then again you can check it with the maximum stress with that factor of safety, right? So this will finally give you the sigma 1 max and tau max as this 0.5 20 upon factor of safety. So this way you can calculate the stresses induced in the case of the force or eccentric load applied perpendicular to the bolt axis, right? And from this you can calculate this simple numerical, right? The following data are given for this bracket into 7.20a. Again, I guess that is what we have seen, that only that shape. So here whatever we have seen, this figure 7.20a is this only, right? So you can now, I guess it will be better for you to correlate, right? So here yeah, the data provided is the load applied is provided, then this eccentricity is provided, then L1 and L2 is mentioned, then there is no preload, right? And the bolts are made of plain carbon steel. Factor of safety is 2.5, right? So using the maximum shear stress theory, so it is mentioned already, right? Because plain carbon steel is ductile material, right? So specify the size of the bolts, right? So what you can do is you can try and attempt this question, right? So how will you start? Again, you will start with this primary force and secondary force, right, which will generate this shear stress and tensile stress. So what is this P1 dash and P2 dash?
6250.
P1 dash and P2 dash equal to 25 kilonewton, right? Yeah, so 6250 divide by 4, because 4 bolts are there, so 6250 newton. Okay, that is correct. Then next, next is P1, next is this P1 double dash, right? So how will you calculate that? See,
Moment about point.
bolts 1 are going to be subjected for maximum force, right? Because it is farthest from that point C. That is clear, right? Here, are you getting what I'm saying? This PEL1 upon this 2L1 square plus L2 square, we need not to calculate for P2 double dash because L2 is less than L1. Yes or no?
Yes.
Yes, sir.
Yes. So this PEL1 upon 2 L1 square plus L2 square. So all the data is with you. You can directly calculate P1 double dash. So what is this?
8108.
Yeah, it is almost around 8108, right? So once you have this P1 dash and P1 double dash, so you will have respectively this tau and sigma t. So tau is the 6250 divided by A, right? And sigma t is 8108 divided by A, correct? So, and you are asked to use the maximum shear stress theory, right? So once you have this tau and sigma t with you, you can find tau max. How you can calculate tau max for MSST? Can anyone? This way you can calculate, right?
Sir, what is tau max of the material?
Tau max is actually given, right? Or from the data you have to calculate, because what is provided is ultimate tensile strength and factor of safety. So from that you can calculate this tau as this 0.5 SYT upon factor of safety. So
Sir,
that will
what
be
are
your
the
tau max. Yes,
value of SYT and FS?
SYT is 380 and FS is 2.5,
Okay.
right? So you can calculate this tau max, that is, anyone?
70.
Sorry,
76, sir.
yeah, it will be 76 Newton per mm square. Yeah, so once you have this, then you can calculate the area, because sigma t and tau both are in terms of area, right? So this will give you area. So what is this?
90.
Yeah, it will be around 98.02. So once you have area, you can equate it to that, what we can say, uh, this pi by 4 dc square, and then you can calculate d, right?
11.17.
11.17, that is dc, huh?
Dia.
So the DC, na, core diameter, right?
Yes, sir. Yes, sir.
Then you have to calculate D. That is DC by 0.8. Point something, right? And then D, which is DC by 0.8. That is
10.96.
sorry,
13.75, sir.
13.75.
13.96. हाँ sir, सही है.
13.96, right? So it is almost coming that M16, right? So actually from area also directly you can come to this M16 if you have that standard design data, right? So this is how you can design your bolt, right? Now the last is this eccentric load in circular base. So here in case of this eccentric load in circular base, as you can see here also you will have this delta 1, delta 2, delta 3, delta 4, right? And here also it will be proportional to this distance L1, L2, L3 and L4, right? So here also the same procedure you can carry out. Here again this force will be proportional to this distance, right? So what you can do is you can again transfer this P into L. Here the eccentricity is given as L, right? So P into L will be equal to this P1 L1, P2 L2, P3 L3 and P4 L4, right? Now again, as we have discussed, this P1, P2, P3, P4 can be replaced with CL1, CL2, CL3, CL4, right? And as previously we have derived, here also you can derive that PL is equal to PL L1 upon L1 square plus L2 square plus L3 square plus L4 square, that you can derive here also, right? Now the thing is, what is L1, L2, L3 and L4? So if you see this figure, then here this L1 is actually this, as you can see, this diameter is 2b, so distance from here to here is b, right? And this angle is given as alpha, so what this angle is given as alpha, and this outer diameter is 2a, which is mentioned here, right? So if you calculate L1, then it will be this a minus
A minus
b
B
cos
cos
alpha, right? So similarly you can calculate for others also. This L2 will come a plus b sin alpha, because here it is again alpha, right? And a plus this b sin alpha will be there. So similarly for L3 and L4 also you can write this a plus b cos alpha, and L4 a minus b sin alpha. So once you have all this, you can put this value, right?
Sir, L3 तो 2a minus b sin alpha होगा ना?
That is similar to a plus b cos alpha. Whatever you say, it is same,
Okay sir, okay sir.
right? Because here it is this alpha, right? So if this b is here, this is alpha, then this is b cos alpha, right, of this 3.3, which is equal to this a plus that b cos alpha, right? Correct?
Yes sir, yes.
Right? So
Yes sir.
once you put all this in this L1 square plus L2 square plus L3 square plus L4 square, what you will get is this 4a square plus 2b square, right? So this is how you will get your equation for this particular P1 as this PL. L1 is a minus b cos alpha, right, divided by this 4a square plus 2b square can also be written as 2a square plus b square, and 2 you can take out as common. Now if you want to generalize this equation, then you can divide and multiply by 2, which will give you this 2 PL a minus b cos alpha upon this 4 2a square plus b square, where 4 is the number of bolts, right? So you can generalize that in case of this circular plate, you can define your that force P1 as 2PL A minus B cos alpha divided by N 2A square plus B square, right? Now here, if you what we can say, go in detail how this force is varying with respect to alpha, then for cos alpha is equal to minus 1, it means when alpha gives minimum value of cos alpha, your P1 will be maximum, right? And at that point, if you write this P1, then it will be this 2PL A plus B. This is maximum, right? Because you are taking cos alpha's value as minimum. So this way you can get this P1 max, right? So this is how you can have this
Sir, P1,
maximum.
P3 will be maximum.
Sorry?
P3 will be maximum, sir.
No, we are discussing particularly for P1, then when P1 is going to be maximum. When this cos
Okay.
alpha will be minimum, at that time P1 will be maximum, right? So for that we have written here. Okay.
Yes, sir. Yes, sir.
Okay. So actually you can also write that alpha in terms of that, what we can say, that 180 minus beta, right? And then that beta is actually going to decide that what are the number of bolt placed in a particular region, right, of that half circular plate. So if you go for that definition of alpha, that is 180 minus this beta, right, where beta is for equally spaced number of bolts. So for that, 180 minus is 360 by 2n, where n is number of bolts. So this will give you that cos alpha can be, if you put this value and give simplification, you will finally come with this cos alpha is equal to minus cos 180 by n. So you can replace cos alpha with minus cos 180 by n also in your this equation, right? So you can write that 2PL A plus B cos 180 by n, right, and divide by this whatever n 2A square plus B square, whatever you have derived, right? So with this you can also see this simple example right here. A round flange bearing as shown in figure 7.26b is fastened to the machine frame by means of 4 cap screws spaced equally on a 300 mm piece diameter. The diameter of the flange is 400 mm. External force is 25 kN located at a distance of 150 mm. Right, 2 double pins to take shear load, right, and the cap screws are relieved, right, of all shear forces. Okay, then determine the size of cap screws if the maximum permissible tensile stress in the cap screw is limited to 50 Newton per mm square. So again here figure this 726.b is this one, right? So let me take this figure for you so that it will be easier for you to calculate, right? So now with this you can start, right, whatever we have discussed. Yeah, so you can see how the different forces will act, right? Yes, so how will you start this? You can find that P1 max, right? Here A is 200 and B is 150, right? As you can see here, diameter is given as 400 and 300. So A and B are radius, right? So A will be 200, B will be 150, number of bolts will be 4, right? L is given as 150 again, right? So I guess everything is with you now, right? In that P1, right? Because P1 is what?
Sir, how was the expression of B2 we got
2PL, sorry,
180.
P cos 180 by N N to B square plus B square, right? So once you have this relation, then it will give you this P1. So here it will be same for all, so we have calculated for only this P1, right? Hello?
Yes, sir.
So can you tell me what is P1? Anyone?
Five five nine eight, sir.
Yeah, it is around almost 5598, right? Newton. Right, so now what you are going to do is you are going to equate this, right, to that stress into area, right? Pi by 4 dc square into stress, which is given as 50 Newton per mm square. So if you go for it, then you will have dc. So what is dc? Yeah, then you can find that shank diameter, right, which is t equals to dc by 0.8. So it will be almost equal to
14.92.
14.92. Okay, so almost 15 you can consider. Right, so this is how you can calculate the size of your bolt required. Then let us see some of the gate questions, right? So in this gate 2001, it is asked that a bolted joint is shown in the figure, right? The maximum shear stress in the bolt A and B respectively are. Right, so you need to calculate first the forces, and then you will be able to calculate the stresses. Correct?
Yes, sir.
Here the size of the bolt is provided already, right? So the very first thing is calculation of this primary and secondary forces, right? So if you calculate this PA or P dash A primary, right? Primary will be same for all, right? This 10 kilonewton by 3. Yes or no?
Yes.
Right. And
Yes, sir.
then yeah, and then in case of this F or what we can say P double dash A, it will be equal to what?
18750.
Okay, but it is this PER A upon RA square plus RB square plus RC square, right? Here actually you are having the values of RA and RB, right? But RA and RC, right? But RB is 0 because the system will have this center of this B only. So RB will be 0, right? RA and RC is given as this 40, right? So you can calculate this by putting the values, this 10 into 10 raised to 3 into this 150 into this 40. Can you hear me?
Yes, sir.
Okay, okay. So here it is this 10 into 10 raised to 3, right, into 150 divided by into 40 divided by this 40 square plus 0 plus 40 square. So it will give you this 18750 Newton. Correct? Yes or no?
Yes, sir.
Yes, sir.
And it is similar to this PC double dash also because both are at the same distance. So now if you consider the forces, see here what is going to happen is this moment will be transferred as F into E or P into E will be in this direction, right? So the stresses generated at A and C, right, will be going to opposing this moment. So if it is in clockwise, then here it will be in anti-clockwise like this, right? And if it is in, no, it will give clockwise, right? Sorry. So this will be at A it will be in this direction, so that anti-clockwise, and at C it will be in this direction, so that again anti-clockwise, right? Here also, here also. So basically what I wanted to say is here this at C and A, the angle between these two forces is 90 degrees, so directly you can get the resultant force at A equals to this PA dash square plus PA double dash square. Correct? Yes?
Yes, sir.
Yeah, so tell me what is this resultant at A?
19043.
Okay, so it is 19.04 kilonewton, right? Here this is Newton, here it is kilonewton. Okay, so now once you have this stress at this particular point, right? This is load at this point. So for stress, how will you calculate the stress? How will you calculate the stress at A and C, right? Both at this both place it is same only. So how will you calculate tau max at A, let us say? This force
PA by
divided by pi by 4
or D.
d square, right?
242.47.
242.5 or whatever, right? 47 megapascal, right? This is at A. So now for B, they have asked you at A and B both, right? So if you go for B, it will be only this 10 by 3 kilonewton, right, divided by this 5 by 4 d square. So what is this? Yeah, it is around 42.44 megapascal, right? 42 megapascal. So from this you can see at point B and A you are getting this 42 and 242. So at A and B it is asked, right? So at A it is 242. So this is correct. Option A is correct, right?
Yes, sir.
Okay. So then the next is this one. So here a steel bar of 10 by 50 mm is cantilevered with M12 bolts to support this 4 kilonewton load, right? Primary and secondary shear load and then resultant shear stress on bolt P, right? So can you attempt this? It is also easy, right? Yes. So calculate this. So primary shear force is 2 kilonewton, right? 4 kilonewton will be divided into both. Yes or no? This primary here P dash and Q dash, right? Let us say force at P dash. I'm directly writing, let us say this Fp dash is equal to this Fq dash is equal to 4 by number of bolts, that is 2 kilonewton. Now it is Fp double dash, let us say. So what is this Fp double dash?
A into R1 by
This whatever this force Pe into R1 by
R1 square plus R2 square.
R1 square plus R2 square. So here what are the different things? Force is given as 4 kilonewton, distance is given as 1.7, 1.7, right? Then
Sir, 159 Pascal आ रहा है.
you are finding force, right? It cannot be in Pascal.
Sir, मतलब 79. Sir.
So this 4 into 10 raised to 3 into this 1.7, right, into this R1 is what?
1800
1800. It is almost near to 20 kilonewton, right?
Sir, yes, sir. FP double dash system.
Actually this 1.7 into 10 raised to 3 I am writing because all other dimensions are in mm. So here the distance will be 200, right? This R1 and R2 both.
How will we calculate the diameter of holes?
E itself is 2 meters, sir.
Sorry?
E itself is 2 meter. From the center of मतलब areas of P and Q.
Okay. It is 1.7 into this 3.
Plus
Right.
1.7 plus 0.1 plus 0.2.
Correct. So actually you can write this 2, right, into 10 raised to 3. Correct?
So how will we calculate R1 and R2? I
R1,
mean diameter of bolts.
R1 and R2 are not diameter of bolt. It will be the distance from this 3, right? What we are going to decide. R1 and R2 are the distance,
Okay.
right? So
yes, sir, 200 and 200.
so yeah, that will be 200, right? 2 into 200 square. So from this you will get this secondary force. So what is this secondary force? This 2 will go, right? This 200 will go, right? Let us say this 200 will go to this, so then 20 kilonewton, right? 2 into 2, where this 20 into 10 raised to 3. Yes or no? Correct?
Yes, sir.
Yes, sir.
Right, so this way you are having the first answer is 2 kilonewton and 20 kilonewton. Yes.
Yes, sir.
Now for the second one, the resultant.
Sir,
Sorry.
sir,
Yes.
so why are we taking the distance from G? We should take the distance from 4 kilonewton, means 1.7 plus 300.
No, why we are taking the distance from G? Because we have already transferred the load at G and the moment at G. That is why we are calculating distance from this point G. In
Okay.
eccentric loading, we are already transferring this load and moment to G. Is it clear?
Yes, sir.
Okay. So now the next thing is resultant shear stress on bolt P. So how will you calculate that resultant shear stress on bolt P? First you have to check the direction of load acting, right, at point P or at bolt P. So if you see at bolt P and Q both, this primary will be in this direction, right? FP dash and FQ dash both will be in upward direction, right, opposite to this 4 kilonewton. But secondary will be in this direction at P and secondary will be in this direction at Q, right? Why? Because it should oppose the moment which we have transferred. So FP will oppose only if it is in this direction, because moment transferred at G is in this direction. Are you getting what I am saying?
Yes.
Yes, sir.
Right, so the total force will now be the 20 kilonewton, right, minus 2
Minus
kilonewton,
2.
right? So 18 kilonewton will be the total force at point P. So if you are having this what we can say, force with you, right, and this M12 bolt is given, so then you can calculate the shear stress, that is 18 kilonewton upon pi by 4, 12 square. So this will be your answer. So what is your answer?
159. 159 megapascal.
Yeah, correct. So this is 159 megapascal. Okay, so this way you can calculate, right? Now if we go to the next one, then here for the 3 bolt system shown in figure, the bolt material has shear yield strength 200 megapascal, factor of safety is 2, the minimum metric specification required for the bolt, right? So what you have to do is you have to calculate this particular diameter of bolt. So how will you proceed in this case? So first, what is the design stress that you can calculate, right? What is the maximum variable stress can be achieved from that, this 200 megapascal divided by this factor of safety, right? That is 100 megapascal, that is the stress, right? Now
Yes,
load acting is given as 19 kilonewton, right? So as load is given as 19 kilonewton, right, and here actually they have asked for minimum specification, right? So here area can be calculated from this force and the stress, right?
Yes, sir.
So you can calculate the area.
Yeah.
So what is the area?
Root of 4a by pi.
Sorry, in terms of this, what you can say, from stress and this load, you have calculated this area, huh?
Okay, sir. Just give me a bit more time.
Uh-huh. It will be 19 into 10 raised to 3 Newton upon, let us say, 100 Newton per mm square. So what is the area in mm square?
One nine zero, sir.
This is 190
Zero.
mm square. So actually this area is required, right? Total area this is required, right? So for one bolt it is A by 3, right? For one bolt. Yes. So you can equate this A by 3 to pi by 4 d square. So what you are getting?
So force should be divided in 3. Why area is divided by 3?
So you can go by that way. If you have divided this force by 3, then no need to divide the area, right? While calculating area of each bolt, if you are dividing this force, this 19 into 10 raised to 3 by 3, right, then you need
Yes.
not to divide this area. But as we have not divided that force, that is why we are dividing area now. Is it clear?
Okay.
Sir, the diameter is 8.97, sir.
Diameter is
But
8.
8.97. Yeah. So it is almost equal to 8.97,
7.
right? So it will be around m10. Okay. So now if we go to the next one, then here also this a cantilever bracket is bolted to a column, right, with this PQR bolts, the value of maximum shear stress developed in the bolt P. I guess this you can do, right, because it is very similar to what we have seen just now,
yes.
right?
Yes, sir. Yes,
So
sir.
Yes, sir.
so we can skip this, right? Yes or no?
Yes, sir. Yes, sir.
Okay. So the next is a bolted joint has this 4 bolts arranged as shown in figure. Cross-sectional area of the bolt is 25 mm square. Torque is 200 Newton meter. Right now, neglecting friction due to clamping force, right? Maximum shear stress in a bolt. So here, as we know, in all bolt there will be same stress. So they have not specifically asked for any particular bolt. You need to calculate what will be the stress. So how will you calculate this? See, all the force acting will generate that moment, right, which will be equated to this particular torque which is applied, right? And as all the bolts are having the symmetry and the equal distance, this 4 PR can be equated to this torque applied, right? So with this you can first calculate the load, right, because as you know that this particular distance is given, r is 50 mm, right, as this diameter is 100 mm, this r will be 50 mm. This torque is given as 200 Newton meter. So the very first thing you can calculate is this force, that is this 200 Newton meter divided by this 4 into 50 into 10 raised to minus 3. I am converting it into meter because this torque is in Newton meter. So you can
Sir,
calculate
1000.
this force, that is 1000 Newton.
Yes, sir.
So once you have that force, then you can calculate the shear stress.
Maximum shear stress.
Yeah.
Force by area.
So this will be P by
That would be
area.
40 megapascal.
Yes, it will be 40 megapascal because 25 mm square is mentioned. So it will be 40 megapascal. So is it clear? Yes or no?
Yes, sir.
Okay. Then the next is here a steel plate is connected to a fixed channel using these three identical bolts A, B and C, carries a load of 6 kilonewton as shown in the figure. Considering the effect of direct load and moment, the magnitude of resultant shear force right at C, so you have to calculate this magnitude of resultant shear force in kilonewton, right, on the bolt C. So can you try this?
Yes, sir.
Yeah, so please try this. See, primary shear force is 2 kilonewton, right, because it is total divided by 3.
Sir, R2 is 0 in this case, sir.
Sorry?
Um,
RB is 0. But you need not to go for RB, you are asked to find for C only.
Sir, primary shear would be 2 kilonewton and the secondary shear would be 15 kilonewton. Therefore, total resultant shear force would be 17 kilonewton. Right?
Sorry?
Answer would be 17 kilonewton, right, sir?
Yeah, correct. Because see, primary on this P dash C will be 6 by 3, right? That is
2. That would
kilonewton,
be 2. Yeah.
right? And P double dash C will be the PE RC upon this RA square plus RB square plus RC square, right? It will give you the answer, correct?
That would be 15 kilonewton secondary.
6 into 10 raised to 3 into E will be 200. RC will be 50, right? And here again 50 square plus 0 plus 50 square. So 2 into 50 square, so 6 into 10 raised to 3, 2 into 50 square, right? So 2 will give this 100, 50 cancel this 50. I guess this 200, this 50, and the 2 into 50 square, right?
It's 12 kilonewton.
12 kilonewton, right?
So the eccentricity should be 250.
Oh, okay. Correct. It is 250 here. Okay. So if it is 250, then 2 into 50 square will be this 50 will go 50 into 200. So it will be 2.5 here. So 2.5 into 6 will be 15. Okay, so 15 kilonewton and 15 plus 2 will be 17 kilonewton. Okay, correct. So all of you are getting the same?
Yes, sir.
Okay, then let us go for this one. So here a rectangular steel bar of length 500 mm, width 100 mm, thickness 15 mm is having this cantilevered to a 200 mm steel channel, right, using 4 bolts. So for external load 10 kilonewton, resultant shear load on bolt P. So this you can calculate, right? So it is easy
Trying
to,
to.
sorry, you can calculate this, I guess. Primary to directly 10 by 4 2.5 kilonewton, right? You are asked to calculate at point B, right? So you can go for this PB dash, that is directly 10 by 4, that is 2.5 kilonewton. Now PB double dash you need to calculate, right? So PB double dash will be this PERB upon RA, RB, RC, RD. Here this R you need to calculate, right?
So 50 root 2.
Yeah, that R will be 50 root 2, and it will be equal for all, right? This R, RA, RB, RC, RD all will be equal to this R, that is 50 root 2. So basically it is PE upon 4R, right? So P is 10 kilonewton, then E is 400, huh?
Yes.
Then 4 into 50 into root 2. That will be your PB double dash. So what is PB double dash?
$14.14 kilonewton.
Sorry?
14.14 kilonewton.
14.14 kilonewton. Okay. So now, but this PB double dash will be acting at an angle, yes? Right, that angle will be 45 degree. Right?
Yes, sir.
So if this is acting at a particular angle, right, and the angle is that 45, then you can directly calculate the resultant between two forces, right? If you don't want to go for those components and all, that PB dash square plus PB double dash square plus 2 PB dash PB double dash cos theta, right? Under root of this is the resultant, correct? So what is this resultant?
2.5 square plus 14.14 whole square plus 2 into 2.5 plus 14.14. Approximately.
So
Would
theta
it
is
be
45
16?
degree.
So would it be 16?
16, yeah, it is almost 16 kilonewton.
So what is theta?
Theta is 45.
Okay.
So it is almost coming 16 kilonewton. Okay, so today we are keeping it up to here.